Okay, in section 1.4, we're going to look at a couple of applications. We're going to look at two different versions of traffic flow, and we're also going to look at some basic circuits. So in this example, we see what is the first type of traffic flow problem we're going to look at, just an ordinary street grid with some one-way streets on it. And what we're interested in doing is determining the values that are possible for these streets that are not assigned. So we're maybe increasing the carrying capacity or changing the carrying capacity of some of these streets to meet the needs of the traffic flow. There's one key feature that we need to know, and that is we need to know that the traffic flow into an intersection is equal to the flow out of the intersection. I think this kind of makes sense. Flow in equals flow out. Obviously, if we've got cars coming into the intersection, we want to make sure that all of those cars can exit the intersection. Otherwise, we're going to have some kind of an accident, I think. So we'll set this up using that relationship. And we'll start out by looking at each one of these intersections. So first, let's take a look at intersection A. And we can see we've got 700 cars and 500 cars entering into that intersection. So that's 1,200 cars coming in. And if we look at the two streets that exit out of A, we have X1 and X4 leaving that intersection. So all the cars that come in, all 1,200 cars, have to be able to exit out on one of those two streets. So that means the flow out is going to come out of X1 and X4 together. And again, all of that has to be equal. And we do the same thing then for the rest of these. And we'll go ahead and look at intersection B now. And you've got X1 and X2 entering intersection B. So street 1, X1 plus street 2. And that's going to be equal to the total output. And we know the total output on these streets is 400 and 600. So that's equal to 1,000 cars coming out. For intersection 3, or C rather, we've got 200 and 600, so 800 cars coming in. And we've got two streets to exit on, X2 and X3. So X2 plus X3. And finally, if we look at intersection D, we've got X4 and X3 coming in. And we've got 400 and 600 cars coming out, so 1,000 cars exiting from that particular intersection. So that's our setup, but it doesn't look like something that's very usable from our standpoint in terms of a system of equations. And you'll also note that not all of the variables are present within those equations, but that's okay. We can put them in with coefficients of 0. So let's rewrite our equations now for our intersections, A, B, and C, and D, in a format that's going to be a little more usable for us. So intersection A will look like X1 plus 0x2 plus 0x3 plus x4 equals 1,200. Intersection B will look like X1 plus x2 plus 0x3 plus 0x4 equals 1,000. C will look like 0x1 plus x2 plus x3 plus 0x4 equals 800. And D will be 0x1 plus 0x2 plus x3 plus x4 equals 1,000. And then we can put that into an augmented matrix, run it through a row ref process, maybe an octave, and we would get something that would look like this. So now we've done an RREF on our matrix, and we would get something like 1, 0, 0, 1, 1,200, and 0, 1, 0, negative 1, negative 200, 0, 0, 1, 1, 1,000. And we get a row of zeros at the bottom of this one after it's been row refed. And then we would go ahead and translate that back into some equations that make sense for us. And we would have the following: x1 plus x4 equals 1200. And it's just coincidence that that happens to be the same equation as we started with. So that's from row 1. Row 2, we have that x2 minus x4 equals negative 200. Row 3 says x3 plus x4 equals 1000. And you'll note that there's no leading 1 in the x4 column. We have that row of all zeros, so that's our free or independent variable. And this is good. It's usable at least, but of course we take one more step and we solve for some explicit formulas for x1, x2, x3 in terms of that free variable. So let's take that final step here, and we get that x1 is equal to 1200 minus x4. x2 is going to be equal to x4 minus 200. x3 is going to be equal to 1000 minus x4. And x4 is going to be equal to itself. So now we've got that solved out, and we can actually extract some useful information from this. Each one of these now tells us that there's a little bit of a restriction possibility on x4. We can't take it to be just anything. And if we just draw out what this particular statement here for x2 is saying, it looks like if x4 is too small, in other words, the carrying capacity for that street does not carry enough cars, then we're going to end up with a negative flow, which means, I guess, that somehow cars are going backwards or something like that, which we clearly don't want. So let's go ahead and make sure that we take x4 to be bigger than 200 to make sure that we don't get a negative traffic flow through a particular intersection. And if we look at x1, if I take x4 to be too big, in other words, the carrying capacity for that 4th street is too large, again, we get a negative traffic flow. So this says that x4 has to be less than 1200. And x3 is giving us a similar statement. There, x4 has to be less than 1000. Otherwise, again, we get that negative flow. So we take the most restrictive of all the scenarios. So that means that x4 here will have to be bigger than 200, but also less than 1000. So that gives us a bound on how much carrying capacity we can build into that street. And that's our final statement usually in these types of problems. So you have that 200 is less than x4 is less than 1000. We could also translate that then into carrying capacities for the other remaining streets, but once we have this statement, we've got pretty much everything that we realistically need to develop the rest of that. But we do want to make sure that we get this in here. So expect to be able to, or expect me to ask to put the bounds on that particular variable and go down to that last step.